And today we're going to start a lecture on discrete probability distributions. So far we know what is the difference between discrete and continuous random variables. But now I want you to learn some of the models that let's keep it like that. Some of the models that are already studied that describe some of the discrete or most common observed processes that are described using discrete probability distributions. So again, I'm going to refer back to this diagram in which we have the two main focuses of this course, which is the population and the samples that is coming from the population. So we know that we are studying probability because we want to be able to describe the population based on a sample taken from this population, and by the end of the course, we want to be able to use some models to describe the population based on the sample. Okay, so this is the process, the ongoing process, and the learning experience that you're going through in this class. So we're still in this area. We are basically using some probability models to describe or to make a prediction of how the sample will describe the population. So the IE 3320 objectives, again, we're still in the second objective, which is use probability models to describe the uncertainty from the population to make decisions. Our map, we started by looking at the measures of location from statistics perspective, the mean and the variance. Then we went through the process of describing a sample space and the event from sample space. Then we described what is a random variable. And from random variable, we describe the probability distributions that can be used to describe these random variables. And we know that we have two groups. First group is discrete, second group is continuous. Okay? And from these two, we can also have joint probability distributions. So in the video lecture that you watched during the last week, we basically went from here. We used the concept that we already learned from statistics to describe the mean and the variance of random variables. Okay, so that's what you did last week. Today, what we're going to do is we're going to focus on the discrete probability distribution, and I'm going to show you some of the most common used probability distributions. And we're going to start with the binomial and the hypergeometric. So today, the material for this lecture is in chapter 5 of your textbook, Discrete Probability Distributions. So I'm going to give you an introduction and motivation for studying these probability distributions. And also, I'm going to describe two of them, the binomial and the hypergeometric. Okay, so the learning objectives for the lecture today is to understand the assumptions for each discrete random variable presented, select the appropriate discrete probability distribution to calculate probabilities of specific applications, and finally, we should be able to calculate probabilities and calculate the means and variances for each probability distribution presented. Okay, so let's go through the introduction and motivation. So, as engineer, you will be frequently working with data that can be modeled as one of the several known probability distributions. So these models are already studied, they have some derivation that goes behind them, and they are used to describe specific scenarios or experiments that are very common. Okay? So again, we're going to start with discrete probability distributions. And these models are able to model the data and allows us to model real systems, design, and predict results. Okay? So the key discrete probability distributions include the binomial, the negative binomial, the hypergeometric, and the last one is the most used, is the Poisson. Okay? So at the beginning of this course, we started discussing how to create this type of representation. Do you remember how this goes? Well, it's right there. This is a histogram. And the idea with these histograms was to represent the shape of the data that we had based on the experiment. Okay? So based on that shape, let's say you got some data, you plot that data using a histogram, and that data would show a specific shape based on your information from the experiment. Okay? So using this shape, you can find a function that will fit that curve or that form. That curve is the probability model that's representing the behavior of the data. Those curves, there are many of them, but the ones that are more important are the ones that we're going to be discussing in this course. Okay? So we're going to focus on those models. Models are called the binomial, negative binomial, hypergeometric, and Poisson. Okay, so we describe the behavior of the data, the shape of the data, and based on the form of the curve that you can draw above the data is the model that you can use to describe the behavior of the data. Okay, so let's take a look at some examples of some known probability distributions. So some distribution describes several real-life random phenomena. So for example, in a study involving testing the effectiveness of a new drug, the number of cured patients among all patients who use the drug approximately follows a binomial distribution. Okay, so if you want to describe an experiment that is like this one, you can use a binomial distribution. Another example, when a sample of items selected from a batch of production is tested, the number of defective items in the sample usually can be modeled as a hypergeometric random variable. So as you can see, these are two different examples. Those experiments can be modeled using two different distributions. And it's because those experiments are different and the properties of those experiments are different. And we're going to explain what are the difference between those distributions in a minute. Another example, some distribution describe, for example, here the number of white cells from a fixed amount of individuals blood sample is usually a random and may be described by a Poisson distribution. Okay? So this is a more healthcare type of example, but again, this is a counting process, and most of the counting process are described using the Poisson. And we're going to go over the Poisson distribution later in this class. Okay? So again, what we're going to do is based on the experiment, you want to model the behavior of the data using a probability model. So let's start with the binomial distribution. Okay, does anyone remember what is the Bernoulli trial? We discussed this early in this course. Bernoulli trial. Correct. So it's an experiment in which you can have 0 or 1 as your result or as your outcome. Okay? So an experiment trial with two possible outcomes, success or failure, is a Bernoulli trial. For example, if you inspect tires coming off the production line, you can classify each as defective or non-defective, and you can define success as a defective tire found. Okay? So if the statistical data shows that 95% of all tires are defect-free, then what will be the probability of success? 0.05 or 5%, correct? So that will be 0.05. Now, in a Bernoulli process, we have n repeated trials. The outcome may be classified as success or failure, and the probability of success, P, is constant from trial to trial, and you can repeat these trials as many times as you want. These trials are always independent. Okay? So we are looking at Bernoulli trials, and I'm going to explain in a second why the Bernoulli trials are important for our first distribution. So let's look at this example. Here we have the chance that a bit transmitted through a digital transmission channel is received in error is 0.01 or 0.1. So that probability is 10%. Assume that the transmission trials are independent. Let x be the number of bits in error in the next 4 bits transmitted. So we're going to look at the next 4 bits, and we're going to find out from those next 4 bits how many of them are errors. And we are interested in knowing from this experiment what is the probability that the number of error is exactly 2. Okay, so that's the question. So we're going to determine what is the probability that x equals 2. So let's define a random variable here, and we can describe this outcome based on these letters. So let's say E is the bit in error, and O is that the bit is okay. Okay, so we're going to use those 2 letters. And if you can see this table, what I'm doing here is just describing the sample space for this experiment. So we're going to have 16 sample points, and each one of them is described based on the next 4 bits. So the first one, for instance, is 0000. That means that the 4 bits or the next 4 bits are okay. The second one is the first 3 are okay, and the fourth one is with an error. Okay, so the outcome of the experiment can be represented with 4 letters. Okay, so for example, if we have this outcome, E-O-E-O, that means that the first and third bit are errors, right? Remember, this is coming from our discussion on the sample space and how to determine the sample space, how many outcomes we have based on the experiment, and how can you represent the outcomes. So we can represent the outcomes for this experiment. We have 4 bits. You're gonna look at all the combinations that can happen for that specific experiment. In this case, we have 60. Okay? So the corresponding values for X are presented in the table. So we are defining X, or our random variable, as the number of bits that will contain an error. So if we look here, for the first one, there's no error, so that value for the random variable is 0. But for this one, we have 3 errors, so the random variable value is 3. For this one, we have 2 errors, E0, E0. So the random variable value is 2. Okay? So the value of the random variable is described based on the number of errors. So the event that x equals 2 consists of 6 outcomes. And we can list those outcomes. Okay? Those will be E, E, O, O, E, O, E, O, right there. Those are the possible outcomes in which you will have a random variable equals cheese. Any questions so far? Okay. So what would be the probability of this outcome? What is the probability of E, E, O, O? How do you find that probability? So we have 4 independent events, right? There are four trials, one after the other. Each one of them is independent. This outcome specifically is 2 E's and 2 O's, which is 2 bits as errors and 2 bits as no errors. They're okay. So if you have independent events, how do you find a probability of 2 events happening that are independent? Correct. You multiply the probability. Okay? So if you have 3 events that are independent, how do you find the probability? You multiply 3 of them. If you have 4 events that are independent, you multiply all of them. Okay? So, for this case, what would be the probability? What is the probability of E times the probability of E times the probability of OK times the probability of OK? What is the probability of having an error? It's 0.1. So this is 0.1. What is the probability of having an error? What is the probability of the bit OK? 0.9, correct. Times 0.9. So that would be the probability of that outcome. You have to multiply the independent events, and based on the specific outcomes, two that contain errors and 2 that do not contain errors, then this specific outcome, the probability is 0.0081. Okay, so that's for 1. Now, if we want to find the probability of x equals 2, what do? You have 0.0081. That's just for 1 outcome. But you know that you have 6 in which you're going to have x equals 2. So I hear something around here. But you said, anyone? Correct. Why is that? Because you have 6 of them, right? And you know that each outcome will have the same probability. So it's the same as saying you're going to sum 0.81 plus 0.81 plus 0.81 for each one of the outcomes in which x equals 2. But since you know that there are 6, you can just multiply this times 6. So that probability, So the probability of x equals 2 will be the summation of those 6 outcomes plus 6.0081 plus 6.0081 and that is equal to 0.0486. Okay? So the probability of having 2 of those 4 bits being an error is 0.0486. So you see what we did? We described the whole sample space. We know from the sample space which outcomes will have a random variable equal 2. And then based on that, we can find the probability of one of those outcomes, which is 0.0081. Since we have the probability of one of those outcomes, then the only thing that you need to do is to find what would be the probability for all of them. In this case, we have 6, so we just add this probability 6 times, or multiply times 6, and you will get the probability of x equals 2. Okay? But this is a very long process. Okay? So that's why we need to define some models that will help you to compute this type of probability very efficiently. And that model specifically for this type of problem is called the binomial. Okay? So in general, that probability, or the probability of x being equal to x, for this type of problem in which we have independent trials, and we have a probability of a Bernoulli random variable in which you have only 2 outcomes, okay, success or failure, then we can have a model like this. So it's the number of outcomes in error times 0.1 x times 0.9 for minus x. So this is the general model for this problem. So you're going to multiply the number of outcomes in error times the probability of a success to the power of x. X is the number that you're looking for, or the probability for the random variable, times 1 minus p to the power of 4 minus x. Good question. I was waiting for that question. Thank you. So we only have 4 bits that we are observing. So that's why we are limiting to 4. Okay? Really good question. Didn't say that, but yeah, I was expecting the question. Thank you. So the number 4 is, this will be n because we are observing the next 4 items. Okay? Any other question? Okay, so let me summarize this. To complete the formula, we need an expression for the number of outcomes that contains x errors. So one group of size X contains errors. Other group of size n minus x contains no errors. Okay, so we have two groups from this sample. We have a group that has errors, and we have a group that has no errors. So, what will be the probability of the ones that have errors? So the probability of the ones that have errors based on this problem is 0.1. But since we are defining this as the probability of success, we can call that P. But going back to this, we know that the number of ways of partitioning for objects in two groups, one of which is of size X, is, so if you want to partition 4 objects into 2 groups, do you know a way to compute that partition? Do you remember from your first exam how to compute that? We can find that by looking at this. Right? So if you're looking at the number of error equals 2, then we can substitute x by 2. Okay, so again, these are concepts that you already learned from the first part of this course. And we're going to keep using them as we progress in this class. So for the case in which we have, let me just state the formula. So therefore, the probability of x being equal to x is, for this example, is for combination x times 0.1 to the power of x times 0.9 4 minus x. And remember, this equals this. So if we compute the probability of x being equal to 2 using this, that will be equal to the probability of x equals 2 will be equal to 6 if you find 4 combination 2, this equals 6. So it's 6 times 0.1 square times 0.9 4 minus 2, and that equals 0.0486. Which is the same result that we obtained here. Okay? So if we have a problem with these characteristics, Bernoulli trial, independent trials, you're finding the number of success. equals something, probability of x being equal to something, then we can use the binomial, and the general model for the binomial is given here with this expression. Okay, and you see, we can get the same probability. Any questions? So on the next slide, I have the definition for the binomial, but I wanted to show you that based on the concept that you already know, we can get to the same answer. Okay, so that's what we did here. This is based on the concept that you learned on the first part of this class. Now, knowing those concepts, we can get the probability right here. You got here, you explain, you list the outcomes, you want to know the random variable value, you do that, x, that's the value of your random variable, and based on the probability of one of those outcomes, you can get the probability of that random variable being equal to a number. Okay? So this is from the first part of this course. Now, you can do the same thing by knowing the binomial distribution. Okay? So, next, here we have the result. So basically, a random experiment consists of n Bernoulli trials, such as each trial is independent, each trial results in two possible outcomes, success and failure. The probability of the success of each trial is denoted by a constant probability. So in that first example, the probability was 0.1. That probability was constant. Then the random variable x that equals the number of trials that result in a success is called a binomial random variable. And the probability mass function for that random variable is right here, which is the model that we defined. Okay? So if I ask you, and I think we're going to look at other examples right now. If I ask you about the probability of a specific experiment that follows these properties, then you can know that you can use the binomial distribution. Okay? So let's look at the next example. Okay, so here we have a pollution example. I know some of you are environmental engineers, so I think this example will be of your interest. So we have an example of water has a 10% chance of containing a particular organic pollutant. Assume that the samples are independent with regard to the presence of the pollutant. Find the probability that in the next 18 samples, exactly 2 contains the pollutant. Okay? So again, we have the probability of success or failure. Right? The pollutant is present or not. So that's the first thing you need to find out about the problem. So these are Bernoulli trials. Okay? Next, do we have a probability for each trial? Do we? What is the probability? 10%. Correct. So that's the second thing. So based on those properties, we can find the probability for the next 18 samples that we will find exactly 2 that contains that contaminant. So how do we express that probability? So the first thing you have to do is to describe a random variable. So what is your random variable? What would you call a success in this problem? You can describe it with a 1, but basically what I'm looking at is the description of the random variable. I will say this is my success. If I find the pollutant in the next sample, that will be described as a success. Okay? So for this type of problem, you need to define what will be considered a success. So again, if you find a pollutant on the next sample, that will be considered a success. So x will be equal to the number of samples containing the pollutant. That's my success right there. Okay? If you look you were to express this in terms of a probability expression, how would you define or how would you write that down? Is the probability of X something? Correct. The probability of X being equal to 2. And this is very important because you're going to see that from now on, we need to describe that expressions in terms of probabilities. So for the first case is the probability of X being equal to 2. Okay? So we know that the probability of success is 0.1, right? We know the sample size, but we also know total number of samples. What will be? 18, correct. So for the next 18 samples, I want to know what is the probability that exactly 2 are contaminated. That's the question. So this is a Bernoulli trial. And we have independent trials, and we can classify these as success. So we can follow and we can use the binomial distribution. So first thing we need to do is to find the expression in X. So we know N equals 18 and X equals 2. So if you solve this, this is 18 factorial divided by 2 factorial times 18 minus 2 factorial. And this is 153. So the probability of X being equal to 2 is going to be equal to 153 times P to the power of X times 1 minus P to the power of N minus X. So if we substitute the values here, it's 153 times 0.1. X is 2 times 1 minus 0.1 to the power of 16. That is equal to 0.284. 18? Where? Yes, it's 18 minus 2. So the probability is equal to 1.284. Thank you. Yeah, just want to make sure that you're paying attention. Probability will never be greater than 1, okay? So this should be 0.284. Okay, so the next problem is it's a little bit more complex. That's part B. Let me call this B. Determine the probability that at least 4 samples contain the pollutant. And see if we have anyone who is willing to come to the board and write this expression, this one, or this expression. I want someone to tell me this is the probability of this X is something this. Anyone? One point for the next example. Again, right here. So it's the probability that at least 4 samples contain their pollutant. At least 4. Well, not the expression, I just want this portion here. I want you to tell me what is inside this bracket. Think about it. On the first part, is to find the probability that exactly 2, right? So that's why we use the equal sign. Well, the next part is the probability that at least 4. I'll give you another chance to think. Look at it. Are you sure? Nope. That is correct. You need to, yeah. So at least means that at least 4. So you have to include 4 and the numbers that goes above. Okay, so thank you. Oh, remember at the end of the lecture sometime. Okay? So this is how you express the probability. Okay? For that particular example. So B is the probability that at least 4, so this is the probability of X being greater or equal to 4. So now the question is, how do you compute that probability? You have 18 samples, so that means that you have to go from 4 to 18 and add those probabilities. So if you write that using the mathematical expression, we do the summation from X equals 4 to 18 of 18X times 0.1 X times 0.9 18 minus X. But what happens? You have the decision this point. Anyway, you go, you can solve this problem. Well, here we have a line from 0 to 80. And we are here, 4. So this is 0, 1, 2, 3, 1, 2, 3, 5, up to 80. If you're trying to solve this problem, you need to find the probability of everything that goes beyond 4, including 4. So that means that you need to sum from here. So this is the probability of X being equal to 4 plus the probability of X being equal to 5 plus up to the probability of X being equal to 80. And as you can see, you have to solve how many? 14 probabilities to get the answer. But you have another option. You can look at the complement. And instead of adding all this, you can look at 1 minus the probability of X being less than 4. Which is essentially this. The only thing that you're doing is, and instead of computing all this, you're going to compute, I have another marker, this area, and then subtract that area from 1. That should give you the same answer. So what we're going to do is this. You're going to look at the complement, okay? So you're going to look at 1 minus the probability of X being equal to 0, probability of plus the probability of X being equal to 1, plus the probability of X being equal to 2, plus the probability of X being equal to 3. And that should save you some time in terms of the computational. So, going back to this, then we're going to look at the complement, and you see why. It's going to save you some time in terms of the computations, but if you go this way, you can get the same answer. Okay, that doesn't mean that the problem is incorrect. The thing is that instead of, if in this problem you have, instead of 80 you have 100, then you have to go from 4 to 100. Okay, so that will take you a lot of time. So it's, most of the time it's better to look at the complement. So in this case we have 1 minus the probability of X being less than 4 And that will be equal to 1 minus the summation from x equals 0 to 3 of this expression. So again, this is 1 minus the probability of x equals 0 plus the probability of x equals 1 plus the probability of x equals 2 plus the probability of x equals 3. And again, so now for each probability, you need to solve this. Okay? Once you solve that, this is going to be equal to 1 minus 0.15 plus 0.3 plus 0.284 plus 0.168. And that is equal to 0.098. Any questions? Okay, we are focusing on the binomial. We have Bernoulli triangles. Each random variable outcome can be classified as success or failure. We can describe such an experiment using the binomial distribution. We have several types of questions that we might need to answer. First one, probability of being equal to a specific value. Very simple. You state the probability using the binomial distribution and you solve for that number. But when the probability is described as an inequality or greater than or less than, then you need to be sure of how you express this probability. And after you express the probability, then you need to find out what will be the less computational effort for you in terms of solving the probability. Any questions? Okay, so we have one more thing to discuss about the binomial, and this is tied to the lectures that you watched last week. So now we want to know what is the expectation of the binomial distribution. So remember, this is a random variable. The only thing is that we are describing a random variable using a distribution. So the mean and the variance of the binomial distribution can be obtained from the analysis of the independent trials. So we can define a new random variable again using x, where 1 is the trial is success, 0 otherwise. And if we look at the summation of those random variables, that will give you the expectation and the variance for the random variable in general. So if you want to find the expectation of xi, this is the value of the random variable times the probability. So in this case, the probability of x success, which is described by 1, is p, plus the second value of the random variable, that is 0, times its probability, which is 1 minus p. So if we solve this, this equals p. So the expectation for a random variable that follows a binomial equals p. And this is just for 1. Let's do the same thing for the variance. So we can describe the variance like this: x minus mu square times f of x. So this is going to be equal to 1 minus p square times p plus 0 minus p 1 minus p. And if you solve this, this is p1 minus p. Again, you don't need to know the derivation, but if you apply the concepts that you learned on the videos, you'll see that these are exactly the same definitions that we use to describe the expectations and the variance for random variables. So in general, the expectation of x is going to be expectation of x1 plus the expectation of x2 plus up to the expectation of xn. So that is equal to n times p, and that is your mean for a binomial. And we have the variance of x equals the variance of x1 plus the variance of x2 plus the variance of xn, and this will be equal to n times p1 minus p, and that is your variance. So if I ask you to compute the mean of a binomial random variable, the only thing that you have to do is to multiply the sample size times the probability. If I ask you to compute the variance of a binomial random variable, then you use this expression. And on the next example, we have a demonstration. So again, this is the definition. So the mean and the random and the variance for a binomial distribution are mu times equals np, and the variance is equal to npq. Here q equals 1 minus p. So in the example, we have one machine tool produces 1% defective parts. If we assume that the parts produced are independent, what is the mean number of defective parts that will be expected if we inspect 25 parts? So we have, this is a Bernoulli. Each trial is independent. We have a probability that is constant. So we can say that this random variable follows a binomial distribution. So we can find the mean using this. So the mean is just the number of items, in this case is 25, times the probability. So that will be 25%. Same thing, we have identified this process as a binomial random variable. So we can use the expression for the variance to compute that variance. It's 0.2475. One more example, and then we can talk about the exam. See if we can describe these problems. So here we have phone lines to an airline reservation system are occupied 40% of the time. Assume that the events that the lines are occupied on successive calls are independent. So again, independent files. Assume that 10 calls are placed to the airline. So that's our N, that's our sample space. What is the probability that for exactly 3 calls the lines are occupied? So again, we have the word equal, or exactly 3. So that means that we have an equality. Okay, exactly 3. So we can express this part A. Let X denote the number of times the line is occupied. Okay, so that's our success. Number of times that the line is occupied is our success. So we can say that X follows a binomial with n equals 10 and probability equals 0.4. So if we solve part A, we are looking at the probability of being exactly equal to 3. So we can express this as 10 over 3, 0.4 to the power of 3, 0.6, 10 minus 3. That one is straightforward, it's just an equality. You plug in the values for n and the probability, and you get the probability. Now, part B is when I need you to think a little bit more. So here again, what is the probability that for at least one call, the lines are not occupied? How would you express that? At least is the same thing that we discussed on the previous example. So at least is the minimum that you will accept, right? So in this case is the probability of X being what? Greater or equal to 1. Correct. This is, let me call this Z, because now something that you need to observe is here we are calling a success the number of times that the line is occupied. On part B, we are referring to a different type of success. Number of times that the lines are not occupied. Okay? So now we need to define another random variable. Denotes lines not occupied. And again, this follows a binomial with n equals 10, but the probability now is 0.6. So which is the complement of 0.4. So if we state this, this is the probability of Z being greater or equal to 1. As I explained here, if you want to solve this, you know you have 10. It's your samples. So you need to go and find X equals 1, X equals 2, and so on. It is easier to solve using the complement. So this will be easier to solve if you look at 1 minus the probability of Z equals 0. And that is 1 minus 10, 0, 0.6, 0, 0.4, 10 minus 0. And this is 0.999. Finally, how would you answer part C? Anyone willing to come here and solve that part? Or bonus point? What is the expected number of calls in which the lines are occupied? 2 bonus points for the next exam. That's right. I mean, you don't have to if you don't want it. Okay, go ahead. So, expected number. That word should sound familiar, right? Expected. What is the expected value, in other words? So what is the expected number of calls in which the lines are all occupied? Okay. Nobody else wants to give it a try? It's very simple. Okay, so we're looking at the expected value for a binomial. So this equals n times p. This is 10 times 0.4. Right there. Expected number of calls is the expected value. In this case, we are looking at the number of times that the lines are occupied, so you need to use the probability for that random variable, 0.4. N times that probability, that's your expected value. Questions?
That doesn't really correspond to the initial probability. Percent.
This one? It is
4.
4. The expected is based on the number, it's an actual number of items. So if it is 40% of the items out of 10, they'll be equal to 4. It's a good question. Okay, so the expected number out of 10, how many of those will be these? And you have that probability right away here, 40%. So the only thing you have to do is multiply that probability. Okay, so again, go back, review. Let me know if you have questions. I'm going to be available in my office this afternoon from 3 to 5:30. So please stop by and let's pass the exams now.